THD, total harmonic distortion. What is it? What causes it? How do we measure it? I'm Professor Fiore, and I'll explain this to you right now. And here we are with total harmonic distortion. What is the deal with THD? It's something you've probably seen on a spec sheet for an amplifier. So we're going to dive in here, talk about what it is supposed to represent. There certainly are some false notions about what it is. We're also going to talk about how to measure it and some pitfalls, some things to be wary of. All right, where to begin? Well, here's the basics. In a nutshell, THD is just a simple way of indicating the linearity of an amplifier or device, right? Quantifying it, putting a number on it. Usually it is expressed as a percentage, and the smaller that number, the better it is, right? The superior or the more high fidelity, let's put it that way, that the amplifier is. Sometimes we don't really care. For example, in a guitar amplifier, we might actually like harmonic distortion. Gives it a different sound. But when it comes to critical playback, monitoring, hi-fi, that kind of stuff, lower the better. That's what we want to concentrate on. So as I said, this is usually given as a percentage, but sometimes it's given in a decibel value. In other words, the amount of distortion that you have in terms of decibels below the total signal. Now, to be accurate about this, the way it's measured, it really should be called THD plus N. N stands for noise, because we don't normally sort of filter out the noise that's in there. We look at this sort of larger spectrum, okay? So, yes, it's THD plus N, total harmonic distortion plus noise, but most people just say THD, total harmonic distortion, right? Just one of those little sort of quirky naming things. Now, where does this come from? Well, if you have a perfectly linear system, a perfectly linear amplifier, it has no distortion. But, that's sort of the holy grail of design, right? All amplifiers have some nonlinearity, so they do create distortion of the waveform. Harmonic distortion is the simplest form. Essentially what happens is we throw in a single test tone, like maybe 1 kilohertz, and the nonlinearity creates harmonics. Harmonics being integer multiples of that input frequency. So I have, for example, a 1 kilohertz sine wave. The distortion mechanism inside the amplifier, the nonlinearities in the various devices and so forth, will create new signals, much smaller in amplitude, but new signals that are integer multiples of that original. So that means 2 times that, or 2 kilohertz, 3 times that, 3 kilohertz, 4 times that, 4 kilohertz, and so on and so on and so on. All right, so yes, you put in a 200 hertz wave, and there's going to be the original 200 hertz at the output, but there's also going to be some 400, and some 600, and a little bit of 800, and a little bit of 1000, and on we go. All right, so they're integer multiples of that input frequency. All right, in other words, you can think of this as just a whole bunch of little sine waves. The thing about the THD spec is there are a lot of variables going into this thing. The greater the nonlinearity, yes, the worse the number, but what ends up happening, how does it get worse? How does it increase? Basically, you get more harmonics, and the harmonics are at higher amplitudes. And the key here is the T in THD. T is total. So essentially what we do is we sort of collect up all of these sort of aberrant little harmonics. We lump it all together into a single number represented as a, like I said, typically percentage of the total signal. So if you have a THD spec that says, well, it's 1% THD, we're saying that of this output signal, maybe that's going to my amplifier, 1% of it is stuff that we didn't put in, right? In other words, I put in a 1 kilohertz signal, coming out as a 1 kilohertz signal, but there's also a little bit more. That little bit more represents, in this case, 1% of all of that stuff, okay? So yeah, you think of it that way, it's obvious that a smaller number is better. It's not a fixed value, though. THD will fluctuate. It will depend on the frequency you're testing. It will depend quite a bit on the output level of your amplifier. And how that happens is also a variable depending on the kind of amplifier you have. You'll discover that like a Class A amplifier, the distortion that you get according to level will behave a little bit differently than it does for a Class B amplifier. And I'll talk about this momentarily, right? But there's a lot of sort of variables that you have to consider here, all right? A lot of people think of THD as this sort of single number that tells you about the sort of pristine quality of the amplifier. It's trying to do that. It's a sort of a coarse measure, right? We're quantifying this complicated system, all of these nonlinearities, down into a single number, right? And whenever you do something like that, subtlety is going to be lost, all right? There are also some gotchas in here. A specific one I want to point out is you should always be aware of the test frequency that's going to be used for any sort of THD spec. That will make a difference. And I'll explain why in just a second. So moving along, how do we measure this? Well, there's basically two ways of doing it. Classically, the way you would do this is you would get a very pure sine wave source. In other words, a signal generator that is designed to produce very, very, very low, very pure, ideal sine waves. You throw that into the amplifier. Now, coming out of that amplifier, of course, will be the original signal plus all these harmonics. So what we then do is we run this through a very tight notch filter, and that notch filter will be tuned to the input frequency. So if I have a 1 kilohertz test tone, my notch is tuned to 1 kilohertz. Coming out of that filter, the only thing you'll have will be the harmonics plus the noise. Okay? Now, what we do is we take that signal, that harmonics plus a little bit of noise, and we run that into a meter that just reads the RMS value. And we calibrate it so that it reads out as a percentage of the input signal. And that's all it is, right? It's just this lumped value that you get. Now, another way of doing this is through Fourier analysis. So this is, made possible essentially by the inexpensive digitization that we have nowadays. But, going back in time, back when I was in college, that long ago, back in the Pleistocene, you would get, if you wanted to do distortion analysis, you would get a very low distortion sine wave source from a manufacturer like maybe Tektronix or Hewlett-Packard back in the days when Hewlett-Packard was the go-to for test equipment, not at all what it is anymore. And then you would get a distortion analyzer, right? So you'd set up your stuff. The distortion analyzer would include inside of it an adjustable notch filter. And if you had a nice one, I remember we had an HP, there was a little switch on there and it would automatically tune the filter for best result. In other words, all you had to do was sort of manually get the filter sort of coarsely tuned to where you wanted it. And the circuitry inside was smart enough, so to speak, put smart in quotes, but smart enough to determine the exact frequency and slightly alter its own tuning to give you the best result. In other words, to completely null out that input frequency. And then it would send that signal off to an RMS reading meter, all right? And you'd have your percentage. It was that simple. Now, here's an interesting thing. You've taken this amplifier and you've reduced the value down to a number, right? 0.1%, 0.01%, 2%, whatever it works out to. I can have two amplifiers that have the same exact value. In other words, they could both be 0.5%. But when we drill down and look at the individual harmonics that are being produced, they can be entirely different. I like to call that a distortion fingerprint. Now, I'll give you a very quick example of this. Amplifier number 1, right? So this black bar here represents the amplitude of the test frequency, right? So I'm putting in, let's say, 1 kilohertz, which is a very common test tone to use. And I get some amplitude for that, right? coming out of the amplifier, I have all of these distortion harmonics, right? 2 times that frequency, in this case 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz, 6, and so on and so on. All right, so all the blue lines here would be the harmonics. Notice in this case that the even harmonics tend to be the bigger ones. Now, although theoretically this can go out to infinity, practically speaking, maybe the first 5, 6, 7, maybe 10, depending, harmonics are really the important ones because they tend to just keep getting smaller and smaller and smaller and smaller as you go out in frequency. So we usually tend to focus around in here, okay? So in any case, we see that like the 2 and the 4 and the 6 are kind of bigger than the nearby like 3 and 5, right? So this has a lot of even harmonics. And that's the kind of thing you might see in a Class A amplifier because of the asymmetry, the fact that Class A amplifiers don't have half-wave symmetry. So you see that. Compare that to another amplifier. And again, I'm going to assume that these two things have the same THD total, right? When we sum up all of this stuff compared to the whole thing, right? The total harmonic distortion. So here's a second amplifier. Now I've got these in red. Notice that the odd harmonics are stronger here. But again, the idea is that when you sum all of this stuff up, you get the same value as you do over here when you sum up all these. Okay? So yeah, these are not the same. Like I said, this might be a Class A. With the suppression of the even harmonics, largely odd harmonics, that's the kind of thing you would typically see in a Class B amplifier. Moving on. So here's a block diagram of your classic distortion analyzer, right? You start off with this ultra low distortion source. DUT is the device under test, preamp, power amp, whatever the heck it is. We run it into this notch filter, right? That gets rid of the original input signal. What's left is the distortion plus noise. We run that into this RMS reading meter. Now, you might also have, and this is generally a good idea, you might also have maybe a C weighting filter in here. Why would you do that? Well, some of these harmonics might be outside the range of human hearing. So a C weighting filter would basically be like a bandpass filter that would get rid of everything below 20 hertz and everything above 20 kilohertz. You don't really want to measure stuff outside that range because you can't hear it. And earlier I referred to, you have to be careful about the frequency that you're using for the test. What does it mean to talk about total harmonic distortion when your test frequency is above 10 kilohertz? Think about that for a sec. Where are your harmonics going to be? F is 10 kilohertz, so 2F is 20 kilohertz, 3F is 30 kilohertz, 40 kilohertz, 50 kilohertz. These are all tones that are outside of normal human hearing range. Even 20 kilohertz, unless you're a young person with good hearing, you probably can't hear 20 kilohertz either. So what does it even mean, right? It's kind of a useless measurement in that regard. So, if you had like I said, a C weighting filter, that would come out and drop out here. And now you could compare two amplifiers, one that had, a wildly different sort of fingerprint than another, but they're going to work out the same in this particular measurement. The other thing is the noise. If you have a wide bandwidth amplifier and you don't have the weighting filter on there, then guess what? All of that noise gets thrown in and it makes that amplifier look worse. And it's only because it has a wider bandwidth, but you can't even really hear the wider bandwidth. So, it's kind of being penalized unfairly. All right. Okay. Let's take a look at a real circuit. So I've got a very simple little Class A amplifier over here, small signal amplifier. I have no swamping. So this thing is going to produce some distortion, notable distortion, putting a small signal in, 20 millivolt peak sine wave at 1 kilohertz. And because this is a simulator, we can assume that this distortion out here in this generator is nil. It's nothing. And actually that brings up something important that a lot of people overlook. Getting back to this. This system is limited by how low this distortion generator is. So here's an error that some people will make. Let's say, and I'm going to use very simple numbers. Let's say that this thing has a 1% residual THD, which would be an insanely high number. I understand that. But this is just for simple mental calculation. Now, I would expect something with like 0.001, maybe lower for a quality ultra-low distortion sine source. But let's just say it's 1%. All right? You go through all this stuff. You come out here to the meter, and the meter says 1.1%. 1% here, 1.1% here. Does that mean the device under test, your amplifier, adds 0.1%, right? 1% here, 1.1% here. Is it adding 0.1%? No. No, 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 no. This is not a simple addition. This is a nonlinearity. You can't just subtract out whatever the distortion source value is from this to determine the value of the device under test. That does not work. All right. If that's 1% and this is 1.1%, I don't know, this could be 0.4%, could be 0.7%. It depends on a whole bunch of things. But that's something you cannot do. All right. So in a case like that, if you're going to do, real world stuff, you can't cheat on this and use, sort of a middle of the road quality distortion source and, just subtract the value off of your meter. That's not going to happen. But here back in the simulator, this is ideal, right? This is as close to ideal as you can hope for. So anyway, I've already checked this out. It has a gain of approximately 150, and it is inverting, right? Minus 150. So, we're going to be looking at somewhere in the vicinity of a 3-volt output. And if it was distortion less, it would be a nice perfect sine wave. It would just be flipped upside down, right? It's an inverting amplifier. So let's do a transient analysis and see what we get. All right, so I'm pushing this out a little bit because I want to make sure that everything settles for these caps. So I'm not starting it right at 0, going from 100 to 102 milliseconds. All right, let's bring this over here, open it up a little bit so you can see it better. All righty, get a legend on here. Okay, so right here, this is the output. And if you look at this, you realize, hey, this is not a pure sine wave, right? This area up here is kind of fat and chunky, and the area in the negative is very pointed. And you can also see that the amplitude, the peak amplitudes are not the same. This thing goes beyond minus 3 volts. This thing doesn't even get to 3 volts. The green, this little thing, that's the input signal. So there's not enough resolution to really see that. That's 20 millivolts. Now the maroon, which I'm now going to highlight, so now it's bright red, that's the THD residual. What does that mean? Well, mathematically, since I know what the input signal is, I can subtract that signal, right? This is essentially what the notch filter is doing. I can subtract that from my output signal, and what's left over is the residual distortion. In other words, this bright red thing is what was added to this ideal perfect sine wave to produce the maroon output waveform. All right, how did I do that? Well, in Tina here, I just went over to the post-processor. So let me just open this up and I'll show you what I did. So here's this thing called THD residual. So what you see is, here's the output, right, V out of T, plus 150, because that's the gain of the amplifier, times V in of T. And you might be thinking, hey, wait a minute, you said you had to subtract it. Yeah, but don't forget the amplifier is an inverting amplifier. So if I add the inverting amplifier signal, that's subtraction. So that's how I generated the residual. Okay, that's how I generated this red thing. Now you can notice that this has a really strong second harmonic component. It's not just a second harmonic component. How do I know that? Just check out the peak values, right? So this negative peak value here is about minus 300 millivolts. But over here, it's minus 388. All right, so they're not the same. And the positive, this is like 387 roughly. And I come over here and, excuse me, it's about 314, right? And actually you can see the crosshairs, you can see how this peak is less than this peak, right? If you come down here, you can see how this peak is greater than this peak. And this just keeps repeating, right? There's that, it matches up over here. So here's what's actually going on, right? I know it's a second harmonic because, right, here's one cycle, right, in my output, and then here's cosine. One cycle, two cycles, right? So there's two cycles of this residual in one cycle. So this is the second harmonic. It's a strong second harmonic, but there's a little bit of other stuff in there. Otherwise, if it was just the second harmonic, these peaks would match up right, and they don't, right? I mean, the negatives aren't the same as the positives, and even the negatives going across aren't all equal, and the positives aren't all equal. So there's other stuff in there, okay? But you know, that's what we're looking at. All right. So essentially, you know, we could take this and say, all right, what is this as a percentage out of this total thing? Okay. Great. So what's the other way of doing this? I mentioned Fourier analysis. Well, you can do that in TINA right here. Essentially, what you're really doing inside this is what's called a fast Fourier transform. It's a form of a discrete Fourier transform. And mathematically, it's going to pull apart your waveform for you and show you what the constituent components are. So you just have to tell it the base frequency where to start. In our case, that's our test frequency of 1 kilohertz. All right. And then you have to specify the number of harmonics that you want. In our case, we're going to use 16. It's just it's sort of an easy number. It's going to produce this format, and this is kind of important if you need to look at the phase. It's going to show everything in terms of cosine pieces, right? Cosine harmonics. Okay. So just calculate it. Boom. And I'm going to open this up. So here's the 16 harmonics. Now, if you're looking at this on a small screen, you might not be able to make out these numbers, so I'll just repeat them for you. 0 would be a DC offset, and this is showing up at 900 and some odd microvolts, so we can just ignore that. Number 1, that's the base frequency, right? So when we were looking at the plot there with all the little spikes, right? That's your input frequency. So that's coming in at just shy of 3 volts. It does show a phase of 90 degrees, but again, that's because it's a cosine waveform. So the cosine is 90 out, and then there's another 90 here. There's your 180, right? Because it is an inverted waveform. Okay. The next largest thing, number 2, is at 300 and just about 45 millivolts. That happens to be in phase. And that's what we see. Okay, so here's your cosine. See how it's starting up here? And it's coming along at twice the frequency. And if we actually check these amplitudes, right, we said it was, well, we got some different numbers because this is really the total residual, but we were getting 300-ish, a little over 300 as we were going through here, you know, all depending on which peak we were looking at, right? So this is saying, well, the actual second harmonic is roughly 345 millivolts. Beautiful. Then it goes on and says, well, the third harmonic, which in our case would be 3 kilohertz, is considerably down from that. That's just about 11 millivolts, and it just keeps dropping. All right, and that's, like I said, kind of typical. So we have less than 2 millivolts at the 4 times, and then below that, you know, once we hit 5 times, everything is below a millivolt, just microvolts. You know, and you can see this is just like little residuals of a couple of microvolts. So just the stuff up here, you know, it's the first 4 or so, in this case, anyway, the first 4 or so that are really shaping the timbral quality, if you will, of the distortion, right? What you're hearing, okay? Now, you probably want to be able to plot the distortion versus level, right? This is at 1 input level. This is at a 20 millivolt input level. I would go through this with other inputs, you know, smaller inputs, bigger inputs. As a matter of fact, I want to go as far as I can as soon as the amplifier starts to clip, right? There's no reason to go beyond that. There's no reason to go beyond clipping. So you might see, if you look around, you probably have seen curves like this. So this compares 3 power amplifiers. Now, I don't know what the amplifiers are. Doesn't really matter. But I do know they are power amplifiers, and this is a plot of the output power here on the horizontal and distortion out here. In this case, this is given as decibel values. Okay, so -5, -10 dB, -20 dB, and so on and so on and so on. All right, so we've got a red, a green, and a blue. And what you see is for very small inputs, which are giving you obviously very small outputs, right? Because this is in watts down here. So they're saying, down here, this is just a few milliwatts, tens of milliwatts. We get these appropriate values. And then as the input signal increases, we notice that the distortion for all three of these amplifiers is dropping. And then eventually it bottoms out, and then it has this sudden, nasty increase. What the heck is that? So, this stops at minus 20 dB. 20 dB is a factor of 10. In other words, this represents 10% THD. Up here, this line is 10% THD. Minus 40 is a factor of 100. So this line right here represents 1% THD. So if we went down to 1%, we can see that this blue thing is pumping out about 100 watts. The red one, which is the highest one, is pumping out nearly 200 watts. All right. Again, total harmonic distortion. This doesn't tell us anything about the distortion fingerprint that we were talking about earlier. Just total harmonic distortion. Okay, so why does it do this? Why does it fall like this? It's obvious, hopefully it's obvious, why it's taking off like this. Because now the amplifier is starting to clip, right? You're starting to chop off the top and the bottom of the waveform, so distortion goes up through the roof. And it does so very quickly, okay? But what's happening down here? Well, there's two possible things going on here. Notice this is labeled as THD plus noise. For very small signals, noise plays a bigger role, right? A noise floor is a noise floor. It's a bottom level. So the smaller the signal is, relatively speaking, the noise is higher, right? You're getting closer to the floor. That might be part of this. I don't really know. I don't know what these amplifiers, who made these amplifiers or the kind of circuitry they're using, but that's one possible answer. The other thing is, depending on the topology of the amplifier, you'll see different things. So usually for a Class A amplifier, like the one that we were simulating just a moment ago, you'll see a value that will increase, more like this. You might have an increase at the bottom end here due to noise, but more of a sort of consistent rise in it because the nonlinearities just get worse and worse and worse as the signal grows. Right? If you took that circuit that we looked at a moment ago and you dropped the input to, a millivolt instead of 20 millivolts, you're going to come up with a less distorted waveform. Just that simple. And it's going to sort of gradually turn into, a clipped signal. That signal the part of the signal that was sort of squished, that was sort of fat versus the other side that was really pointy. Eventually that fat part's going to start clipping. It'll be obvious where it limits. So that's what you'd probably see for a Class A. For a Class B, this would be much more typical. Yes, there is the noise issue, but there's also the percentage of crossover distortion. The bigger the signal is, the crossover distortion represents a smaller overall piece because that's kind of a consistent thing, right? Remember, that's caused by the turn on of the base emitter diodes in your transistors. So for small signals, we expect that to be slightly higher. Either way, right, this is what we're seeing. Comes down. This is only 10 watts, okay? At a few watts, 10 watts, 20, 30, 40 watts, we're looking at fairly small values. Well, the question is, well, how low is low enough? Well, I want to point out something, and that's minus 60 dB. Minus 60 dB is a factor of 1,000, and that would correspond to 0.1% THD. Now, you will hear people say, that's a terrible number for hi-fi. It has to be, 0.00000000000001. Insane numbers, right? Golden ears will tell you these things. Oh, it's got to have at least 3 zeros up front. Use your brain. Think about this for a sec. If you were listening to music in your home, fairly loud level, let's say 80, maybe 85 dB SPL. That's pretty loud. I mean, if somebody comes in, they're going to have to talk really loud for you to have a conversation with them. If the distortion is minus 60 dB, 0.1%, that means in your room, it's sitting at 60 dB less, right? So if the average SPL is 80, 85, that means the distortion is sitting at around 20, 25 dB SPL. If you got a SPL meter and you put it in your house, chances are the residual background noise in your home is at least that high. It's probably higher. I'm not saying, you live next to a freeway or you live next to, an airport. It's simple things like the noise of wind outside, leaves in the trees moving, your hot water heater making a hum in the background, things like that. If the distortion is down around the residual background noise, the ambient background noise, you can make a good argument that you can't hear it because it's swamped out by this other stuff. Well, certainly if it's well below that, you're not going to hear it. Now, if you had headphones, you can swamp out that background noise. So you might make an argument that with very high quality headphones, you might need something a little bit less than that, a lower number, but it's not going to be a huge value because don't forget, things like headphones and certainly loudspeakers at low frequencies create a considerable amount of THD themselves. That's really the weak link in your playback system, not the amplifier. Once you get an amplifier, a power amplifier that's below 0.1% across the board, in other words, from a low output to this, pre-clipping output across the frequency range, you test it from, 20 hertz on up. Once you're down there, your problems are largely coming from somewhere else. Okay, there's really maybe it's not the wisest move to sink a lot of money into improving an amplifier that's, let's say you got something that's like 0.05%. Do you want to spend a few $1,000s to get from 0.05% to 0.009%? That doesn't make a lot of sense to me. Especially when you have, your loudspeakers are producing, depending on the amplitude and the frequency, that might be producing a couple of percent THD. All right. So that's just one little piece of the puzzle. Your amplifier is just one part of the whole thing. All bets are off if you're talking about musical instrument amplification. Does your guitar amplifier have 1% THD, 0.1% THD? Who knows? I mean, the thing about that is that's a tool for an artist. You listen to it. Do you like the way it sounds? Maybe it's got 5% THD. Maybe it's got 15% THD. If you like the way it sounds, that's really all that matters. It's not there to reproduce an already existing sound, right? In other words, a recording of some kind of, musical performance. It's part of the musical instrument. You have your electric guitar, you plug it into the amplifier. That whole thing is your instrument. So we tend not to look so much at the distortion of, like I said, something like a guitar amplifier. You might be a little bit more persnickety about that if it was a wide range amplification system used for maybe a keyboard, like you got a piano and you want a really good sounding piano, you're going to use that. Maybe, maybe not. Again, you might like the distortion that it produces on your keyboard sound. But like I said, for a guitar, it's a little bit different than some kind of hi-fi sort of thing. Critical monitoring. I'm going to do a mix down here, and I need something very, very accurate. Okay. Well, I think we've pretty well exhausted this. Is that the end of the story? The answer is no, that is not the end of the story. There's also something called IMD, intermodulation distortion. But that's a story for another day. And until then, this is Professor Fourier saying so long and take care.